Hey guys, I left my thing my Elmo that I usually use to record videos at home, so I'm using my cell phone and you can kind of see the thing I'm propping it up on. But anyway, I apologize. All right, so this is the first lesson for pre-cal, and first we're going to start out with geometry from triangles. So we're going to review some old school material about triangles, and you might remember it from when you were in high school, or you might not, but either way, I'm going to treat you like you know nothing and we're starting from scratch. Okay, so this example says simplify. That means make smaller. And when we make these square roots smaller, we put the pair on the outside and the single guy on the inside. Okay, that doesn't really make sense right now, but in a couple of minutes it will. All right, so first it says square root of 25. Well, what we're gonna do is we're gonna take that 25 and we're going to break it up into things that multiply to 25. And I think the only thing that multiplies to 25 besides a 1 and 25 is 5 and 5. All right. The square root of 25, you probably already know, is 5. But the reason it's 5 is because there's a pair of 5s that multiply together to get that 25. So square root of 25 is kind of like saying square root of 5 squared, and then that square root house and the tiny 2 cancel, and you just get big fat 5. Okay, and you get big fat 5 because it was a pair. Let's try this 50. If I break 50 up into things that multiply to him, we could try 2 and 25, or I already wrote down 10 and 5. Let's keep breaking. 5 is 2 and 5. My bad. I meant to say 10 is 2 and 5. And then what I'm going to do is I'm going to cross out what has been broken. So I'm going to cross out this 50 and this 10 so that I don't accidentally write it down again. Okay, let's find my pair. My pairs are on different branches, but who cares? So that 5 is going to come outside as a single number, 5. Just like from this square root 25, it became a 5. We have a 5 because technically there's a 25 that lives in that 50. Okay, and then there's a leftover 2. That's the single. So the 2 goes inside. And you might have an easier way to do this. Go for it. Do it. Do it. I'm going to teach you something on the calculator in a little bit, but if you already have your own way, go for it. All right, square root of 34, that's 2 times 17. And I didn't really know the 17, but I knew this 34 was even, so I divided by 2. And then both of these are prime. And there's no pair between them. I just see 2 once, 17 once. So unfortunately, since there's no pair, you just leave it like it is. So this sucker cannot be simplified. It just stays square root 34. All right, let's go up to this 72. There's 2 ways to do the 72. Or there's a couple, my bad, there's a billion ways to do 72. But there's a couple of different things that could happen. Okay, first, let's say 72 is 2 times 36. I did not know the 36, but I knew that 72 was even, so I divided by 2. Like in my calculator, I just picked it up and pressed 72 divided by 2. Hey-oh, 36. Okay. And then 36, if you break that up a special way, it's 6 times 6. Cross out what has been broken. Goodbye 72, goodbye 36. Circle the pairs, 6. That goes on the outside. Circle the single, hey, 2. She goes on the inside. All right, so the final answer for this square root of 72 should be the 6 on the outside and the 2 on the inside. But unfortunately, not all of us would have picked 2 and 36. We just happened to work out perfectly with a pair of numbers, a pair of 6. And the reason we got those 6 sixes is because it came from a perfect square, 36. Let's say I didn't pick 2 times 36. Pick something else that multiplies to 72. I think maybe 8 and 9. So break up the 8, break up the 4, break up the 9, and remember, these are things that multiply. Okay, cross out what has been broken. Goodbye 9, 8, 4, and the 72 we started with. Circle the pairs. I see a pair of a 3, so that's going to go out. I see a pair of a 2, it's going to go out. I see a single of a 2, that's going to go in. Okay, let's see how this somehow becomes 6 square root 2. Well, the 3 I take out. The 2 I take out. And then that little leftover lonely single 2 I put in. But this is supposed to be 6. I have 32. Well, let's not forget that all this junk in here is multiplying to 72. 2 times 2 times 2 times 3 times 3, that's 72. 4 times that, that's 72. 4 times 8 times this is all 72. Okay, so the point is we're supposed to multiply. So put a big fat multiply dot in between 3 and the 2, and then hit fire that 6 square root 2 that we needed. All right. So we did it 2 different ways. The first way, we were lucky that we found a pair right away, 6 and 6. But the second way, I just kept going, but we still got a 6 in our answer. Okay, let's look at this 3 over square root of 2. In math, now that we're grown, square roots can not be underneath. They can't. It's not called rationalized. So we need to rationalize this, as in make the square root disappear from the bottom. Well, we don't just erase it. In math, how can you get rid of a square root? We could perhaps square it, or we could multiply by the square root of 2 over the square root of 2. And you're asking, where did that come from? Well, you know, like when you're doing like LCD or something, you know, let's say I have these numbers and I want to add them. To get an LCD, you multiply the bottom by a 3. That way I can get a denominator of 6. And you do it to the top and bottom. Same thing here. Only, so instead of multiplying by just a regular whole number, top and bottom, we're multiplying by the square root, top and bottom. Because square roots are not allowed in math in the bottom. So we get 3 square root 2 over square root 4. But what's the square root of 4? It's just 2. So we get 3 square root 2 over just a 2. And instead of going through all that rigmarole of square root 4, I like to think if you have the 2 of the same square roots, yeah, the square root cancels and you just get whatever the stuff was on the inside. So that's why this square root 2 times square root 2, it's the same square roots. And when you multiply them, they cancel out to just a regular 2, or what's inside. All right, let's look at F. It says 2 over 5 square root 3. Again, the square root 3 is boo-boo. It's bad in the bottom. It can be in the top, though. So we're going to multiply by the square root of 3. This is called rationalizing. You make the bottom rational, as in that square root. A fancy name is called irrational. Square roots are irrational. So when we're rationalizing something, we're making the denominator rational, as in getting rid of the square root. You don't care. All right, anyway, so we get 2 square root 3 all over. On the bottom, we have a big fat 5 already there, times, what did we say? The same square root times the same square root. It's just what's inside, right? So this is square root 3 times square root 3 is just what's inside there. 3. All right, math it out. You get 2 square root 3, and on the bottom, you get a nice, pretty 15. So it's been rationalized. We took that irrational square root out of the bottom, and we made it into a nice, beautiful, rational whole number 15. Okay, let's look at G. Again, square roots in the bottom are no bueno. But we have 2 square roots. Who cares about the top one? Square roots in the top are okay. They're totally okay. It's when there's a square root in the bottom that it's no bueno. So we're going to multiply by the square root of 5. And remember, so that the square root in the bottom will disappear. And remember up here, what did we do? Oh, we said square root of 2 times square root of 2 was you just multiply them inside 4. Same thing here. The 7 is the whole number on the left, and then square root 2 times 5 is square root 10. So you just multiply inside the square roots. Okay, on the bottom, we have a big fat 3 times the same square root times the same square root. 5 times 5 makes 25, but then you have to square root it, so it just pops out a regular 5. All right, and then we get 7 square root 10 over 15. If we could, we would try and reduce this 7 and 15, but we can't. Yeah. Okay, you might be asking, can I reduce what's inside the square root, like this 3, with what's underneath? No. Can I reduce the 10 and the 15? No. This square root is like a barrier. You cannot ever go into the square root. Don't ever mess with what's inside unless you're doing this tree branch thing. That's the only messing we're doing. Okay. So this 3 and 15 do not reduce, because the 3 is inside of a square root. It's inside of a house. It's protected. Okay. This 10 and 15 do not reduce. You know, maybe if I would have had 21 square root 10 over 15, then I could then I could reduce the 21 and the 15, but not the 10 and the 15. So you can reduce the numbers outside the square root, but not in. So this 21 over 15, I think you can divide them by 7, and you'd get, no, you can divide 21 and 15 by 3. So you'd get 7 square root 10 over 5. So that's if you could reduce the numbers on the outside. All right. Let's try a big one. Square root of 360. That's massive. Okay, we could do this a couple of different ways. We're going to do the tree branch thing, and then I'm going to show you something in the calculator. Okay, if I branch it off, let's do things that multiply to 360. Let's try 2 and 180. If you would have chosen, actually, there's 3 ways we can do this. Okay, or multiple ways we can do this. Let's say I would have chosen 36 and 10. 36 is 6, 6, and 10 is 5, 2. You cross out what has been broken, and you find the pairs. The pair of the 6 goes out. The singles of 2 and 5 go in. So we have 6 square root, and then that 5 and that 2 go in. But when they go in, don't forget that all this junk, all these numbers from these branches are multiplying up to 360. So this 5, 2 needs a multiply dot in between. And then we get 6 square root 10. Okay, let's accidentally do too much, okay? So our answer is 6 square root of 10. But let's say I did not use 36 as one of my multipliers, because this 36 broke into 6, 6, and it was awesome, right? Awesome, awesome, awesome. Let's say I tried 2 and 180. All right, let's see this. 2 and 180 is 2 and 90. 90 is 2 and 45. 45 is 9 and 5. 9 is 3 and 3. Okay, let's see how I could get 6 square root 10 out of that. Cross out what has been broken. 360, 180, 90, 45, 9. Circle the pairs. I got a pair of a 2, it goes out. I got a pair of a 3, it goes out. But remember, they multiply. I have a single of a 2 and a single of a 5. Those go in. But remember, they multiply. So in the end, 2 times 3 is 6. 2 times 5 is 10. And hey, look at that. Okay, so if we accidentally went too hard and did not have 36 anywhere on our paper, then just don't forget, multiple pairs multiply, or multiply. So put multiply dots. Okay. Let me show you something in your calculator. And yeah, in our calculator, I think these steps are in your lesson 1 reminder handout. Let me see if I can find it. Here it is. Here's your lesson 1 handout. It's from Blackboard under reminders. And we're about to look at the bottom right where it says in graphing calculator press. Okay, so it says in graphing calculator, press Y equals, so this top left button. Okay, let me clear. And it says then the number, this one says 98, but our number is 360. So we're going to type 360 divided by X. So I pressed Y equals, then 360 divided by, and the X is that XT theta button. Okay. Then it says, then second graph. So second graph is this guy. Yeah. This is for if you don't want to do the tree branch thing. Okay, so I see second graph. And now I'm going to look for the perfect squares over here on the left side, the x-axis. So perfect squares are, let's see, 1 squared is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. You get the point. Okay, so what we're going to do is, the reason we're just looking for these perfect squares is because we're trying to find a shortcut. If you remember back to 360, 360 is the same thing as 36 times 10. Well, 36 is the biggest perfect square that can divide into 360. So a shortcut is to use our T-chart in our calculator and look for the perfect square and find the biggest one. Okay, let's see. Across from 1 is 360. 4 is 90. 9 is 40. Let me keep sign. And some of these are decimals. 16 is a decimal, so I don't want it. 25 is a decimal, so I don't care about it. 36 is 10. 49 is a decimal, so I don't care about it. And then if you kept going, all our perfect squares after this 36 are going to be decimals. So let's see, what's the next square? 7 squared is 49. 8 squared is 64. And look at 64. It's a decimal. What's 9 squared? 81? Well, let's look at 81. Oh, it's a decimal. Okay. So, we're going to toss out the decimals. But goodbye. Okay? And then out of this 14936, which one's bigger? 36 is the biggest perfect square. Okay, so let's see here. 360 is the same thing as 36 times 10. And then the 6 comes from that square root of 36. The square root of 36 is a 6, and then that 10 stays in because you can't square root it. And heck fire, that's the same answer I got these other 2 times. Okay, so if you're having trouble with the tree branches, try typing in your calculator, pressing y equals, and then typing whatever your number is, divided by the x. Go to your T-chart and look for your perfect squares on the left. And on the right, if they give us decimals, toss them out. And yeah, okay. And then whatever the biggest perfect square is, for example, 36 is bigger than 9, you use that 36 and 10, and then you take the square root of what you can. All right. Okay, let's go again. Now that we've talked about square roots, let's talk about the Pythagorean theorem. The Pythagorean theorem is at the top right of your lesson 1 handouts. And the actual theorem is this equation, a squared plus b squared equals c squared. And you use this when you want to find the third side if you already have 2. And on these triangles, I have 2 sides and the third is missing. I have 2 sides and the third is missing. Okay, it says the legs can be called the height, the base, the altitude, the adjacent, or the opposite. Never the hypotenuse. And then it says little c is always the hypotenuse. The a and b can be switched, that's okay. But the hypotenuse is always this crookedy part across from the 90. A and b, I can label those like BA, AB, it don't matter, but she always has to be the hypotenuse. Okay. So, let's fill out this formula. Let's see, I got a squared plus b squared equals c squared. And the hypotenuse is what is missing. Well, what letter is the hypotenuse? The hypotenuse is always the letter C. Okay? So that means we don't know the C, so let's keep it the letter C. And then 5 and 7 can be interchanged. It doesn't matter which one you put. 5 squared plus 7 squared. And then PEMDAS says we have to do exponent first. So let's exponent this. 25 plus 49 equals c squared. Okay, PEMDAS says PEMDA, add. So let's add this stuff. Don't judge me. I'm not that great at addition or subtraction. Okay, we get 74 equals c squared. Okay, then to get rid of that tiny 2, you put a square root on it. What? And then we have to break up that 74 like we were doing up here, or we have to try to. So let's try and break the 74. 74 is even, so I know 2 times something goes in there. 2 times 37. And then 37, 37 does not break down again. It's prime. So this is like example C, where when you break it down, all you get is pairs. I mean, all you get is primes. And those primes, there's no pair there. So you just leave your answer the same. So since there's no pair, because they're all primes, 2 and 37, you just leave C as square root 74. Yeah. And we always want to leave it with the square root. The only time we ever type this in the calculator is when the homework says something about approximate, estimate, guesstimate, round, something about decimal spots. Yeah, you get the point. So always type in this dirty square root answer. All right, let's go to B. It looks like I have the same numbers, right? 5, 7, 5, 7. And the math is going to be similar, but this 7 is not going to be where the B is anymore, because let's see, 7 is the hypotenuse, and hypotenuse is always C. Yeah, so and then we don't know the base. So let's say a squared plus b squared equals c squared. So I'm definitely going to have 5 squared plus, I guess, b squared we could use. Just the letter b, since we don't know it. This is bond piece. And then c is always the hypotenuse. And you can find the hypotenuse because it's the crooked piece. But I mean, if I put my paper like this, all the lines look crooked. So another way to think of it is, it's across from the 90. Yeah, so the hypotenuse is always across from the 90. I forgot my squared. Okay, let's exponent from PEMDAS. We get 25 plus b squared equals 49. Okay, now instead of a adding, we're going to have to get this b by itself. So we're going to pick up this 25 and subtract it. And we get b squared equals 4. Okay, you got to put a house on that, Wicked Witch. And we got to break up that 24. 24 is the same thing as like 2 and 12. 12 is 2 and 6. 6 is 2 and 3. Okay, cross out what has been broken. Goodbye 24. 12, 6. Yeah, that's all I broke. And now let's find the pairs. I see a pair of a 2 that's going to go out. I see singles of 3 and 2 that's going to go in. And remember, when they go inside, you use a times dot. Times dot. Or if they go outside, you use a times dot. But either way, we multiply. All right, so our C is equal to a 2 on the outside. Square root 3 multiply dot 2, or C equals 2 square root 6. Okay, so the point of this was to show you that placement matters. Okay, your hypotenuse always has to be across from the diagonal on the picture, and your hypotenuse always has to be this letter C. The A and the B, they can swap around, but the C is always that crookedy hypotenuse. All right. The next thing we're going to look at is, if you're looking at that handouts paper on the second page, kind of towards the bottom right, it says something about Pythagorean triples. These are the numbers that work every time perfectly for the Pythagorean theorem. And when I say perfectly, I mean they pop out as a whole number. So these are the sides of a triangle that will always work. Like I could have a 8, 15, 17 from this triple right here. The only thing you got to remember is all these, I think it's the third number. Did they type it right? Yeah. The third number, or whatever the biggest number is, should always be the hypotenuse. So the biggest number in these triples are always the hypotenuse. So in the future, if I saw a problem with 5 and 12 on it, I could skip the work and say, hey-oh, hypotenuse is 13. Or if I saw a triangle with 3 and 5 on it, I could say, hey-oh, the other side is a 4. Okay, let's look at this. It says triple, and I got a side of a 3 and a 5. Okay, well, I know it's a 3, 4, 5, but the 5 has to be the hypotenuse. That's the only way this is going to be a 3, 4, 5. So let's check. Is this 5 a hypotenuse on the first picture? Heck yes, it is. Okay, so that means the 2 legs, or the other sides, are 3 and 4. So I already have a 3, so I automatically know this bottom piece is 4. What? Sorcery. Okay, let's try again. This sucker, it says I got a side of a 4 and a 3, and this crookedy piece is the hypotenuse. Well, every time you have a leg of 3 and 4, the hypotenuse is 5. We didn't even have to do math for that. Okay, let's look at these last two. They are a Pythagorean triple, but we have to do a little sorcery to get them. Okay, let's see here. How do you... Okay, these are called like similar triangles from back in the day. And similar triangles say that if I can take the number 3 and 4 and multiply it by some number, I can do the same thing to the 5. Yeah, okay. So let's see if this 8 and 6 are some kind of 3 or 4 times something. Okay, 6 is not 4 times something. Okay, I need a whole number. So 6 is not 4 times something. Instead, 6 is 3 times the multiplier of 2. That's where we get 6 from. And that 3 is the 3 from the triple, and then we multiplied it by 2 to get 6. Then if you look at that 8, it looks like 8 can come from a 4 from the 3, 4, 5. Only what do you have to multiply by to get 8? 4 times who gives you this 8? 2. So our multiplier is a 2. It's like a scale factor. If we were talking about similar triangles, you don't care. All right, so let's see what this hypotenuse is. Well, I know the hypotenuse of a 3, 4, 5 is 5. Well, I have to multiply it by 2 because that's the multiplier. So 5 times 2 is 10. So we just found our hypotenuse. 10. Yeah, let's look at this 36 and 27. It's another Pythagorean triple, and it does come from this 3, 4, 5. Let's guess how. Well, both of these look like they can be divided by 3, right? Like if I divide both of them by 3, I get 12, but that's not part of the 3, 4, 5. Yeah, okay. So, what else can I divide 36 by? I can divide 36 by 12. Okay, and that gives me a 3. So this side could possibly be the 3 of the 3, 4, 5. Okay, if it was the 3, then I divided 12 to get it. That means I should be able to divide 27 by 12 and get 4. And I don't. Okay, so this 36 is not going to be the 3. Because when I take 36 and divide it by 3, I get 12. That ain't my 3, 4, 5. Okay. So, let's think. It looks like 36 and 27 are multiples of the number 9, right? Just like with 8 and 6, those were multiples of 2. Like 2, 4, 6, 8. Who do we appreciate? Yeah, okay. So 8 and 6 are multiples of 2. And so that was my multiplier, the 2. Well, think about it. 36 and 27, what are they multiples of? They're multiples of 9. So that should be my multiplier. So let's try. 9 times, sorry. So this 36 is either 3 or 4 times 9. That's how we get 36. And then this 27, it's either 3 times 4 times 9. That's how we get 27. So what times 9 gives you 27? 3. So that's the side. Or that's the original side 3 of the 3, 4, 5. So this wasn't originally a 3, and then we multiplied it to by 9 to get 27. What did this 36 have to be originally, so that when I multiply it by 9, you get 36? 9, 18, 27, 36. 4. Okay, so this is a 3, that's the 4, the multiplier is 9. What's the hypotenuse? Well, on a 3, 4, 5, the hypotenuse is always a 5, but then we have to multiply it by the 9. So our hypotenuse should be 45. We're going to use that sorcery coming up after this super easy example. Okay. So the point of that was, if you ever see a triangle, a right triangle, with a hypotenuse 5, the other sides are 3 and 4. You just have to figure out where they are. Or if we ever see a triangle with hypotenuse 53, the other two sides are this. But honestly, we usually only memorize this first and second triple. The rest of them, I never remember them. All right, let's look at this next sucker. Find the missing angle. All right, well, if we're looking at our tricks, it talks about angles at the top left of the first page of that handout. And it says, all triangles degrees add up to 180. If we know 2 angles, minus for the third. So all the angles add up to 180. Okay, let's look. Oh, and it also says right triangles have a 90-degree angle. And that's what this little box is. The little box is 90. Okay, so it says find the missing angle, this question mark. Well, I know all of them added together gives me 180. So 37 plus this 90 degrees plus a third angle we don't know is supposed to equal 180. Okay, another way to say this is take the 180 and subtract the 37, right? Because to get the question mark by itself, we'd have to subtract the 37. Subtract the 37. Okay, so we're going to take 180 minus 37, and then we're going to subtract the 90. Subtract the 90. And that should give us this leftover angle. Hey, 53 degrees. Exciting. Okay, let's look at part B. Again, I know I'm going to take 180 and subtract 47 and subtract 90 degrees because 90 comes from this little box. So let's subtract those. I wrote up and down like I was in 4th grade, but that's okay. We get 43 degrees. Exciting. Okay, let's look at this part C. The awkward part is that it has X's in it, but we're still going to write it the same. We're going to say 180 minus this 3 degrees minus 4x degrees. Okay, We can't really do anything with that x. It's just going to be in my answer. But I can do 180 minus 3. That's 177. Minus 4x. Degrees. Yeah, and I think on your homework, this is maybe like multiple choice or something. It's funky because of the degree symbol. Or maybe it's multiple choice. All right. Let's keep going. Okay, so far we've talked about the legs of triangles, the hypotenuse of triangles, angles of triangles. Now we're going to start labeling the sides of the triangles with something other than hypotenuse. Okay, so for the next couple of examples, it says label the triangle and find sine A and sine B. Okay, well, I got one triangle and it has all the same numbers, 3, 4, 5. We're using the same triangle for both. So you might think that the answers are the same. They're not. Okay, so first what we're going to do is we are going to label this triangle from the standpoint or the viewpoint of angle A. So this angle A is how we're going to identify what is the adjacent and the opposite. Okay, first off, the hypotenuse is always, across from the right angle. And the way we label them with letters, we got to be careful because the opposite and adjacent can change according to how you label things. Okay, if we have capital A and I draw an arrow from that angle to the other side, that's little a. Whereas if I look at angle B and I draw across to the other side, that's little b. And then little c is always the hypotenuse. Okay, so let's see. Little c is always the hypotenuse. And the reason is because it's opposite of that C angle. Okay, now let's figure out what that 4 is. That 4 is opposite of capital A. So it's going to be labeled little a. This 3 is opposite big B. So we're going to label it little b. Okay, now we're going to use the words adjacent and opposite. Adjacent is the side that you're touching. And we already have hypotenuse labeled. So this angle A, what other side is it actually connected to? Besides this hypotenuse, it's actually connected to this little b. So this 3 on the bottom is the adjacent. Adjacent means the one you're right next to, the one you're sitting next to on the church pew. Yeah, okay. This 4, it is opposite, that capital A, opposite. So that 4 is the OPP, opposite. Okay, but what if, okay, we'll just go ahead and do that one. Okay, now we're going to use something called SOHCAHTOA. SOHCAHTOA if you look on the second page of your handouts, your reminder sheets, so starts with an S because it describes the sign. Yeah. So means sign, and then the OH means opposite over hypotenuse. Get it? S for sign, O for opposite, H for hypotenuse. Or if you look at the second page of your handouts, it says sine is O opposite over hypotenuse. Okay, so we're going to use the so part because they want us to find sine. So we're going to use the so. Okay, so sine of capital A. See how you write sine and then the angle, ours is just a capital A, equals a fraction with the opposite on top and the hypotenuse on bottom. And again, O comes from opposite, H is for the hypotenuse. Okay, so what is my opposite of A? Opposite of capital A. Opposite of capital A, we already labeled it. It was a 4. What was the hypotenuse of this triangle? 5. So sine of A is equal to 4 over 5. Sine, cosine, tangent, it just represents a ratio of your sides or a fraction of your sides. That's all it means. You put your sides into a fraction and it means something special. All right, let's look at this sine B. Well, we're still using the same triangle. And the capital A, B, and C and the lowercase a, b, and c are all the same. Yeah. The hypotenuse is still little c, but the part that is different is what is labeled the opposite and the adjacent. Okay, if we look at this angle B, which is what part B is talking about, sine capital B, in relation to this angle, if I draw a cross means opposite. And look, that's different from part A. In part A, that bottom piece is the adjacent. So you can't just willy-nilly start labeling opposite and adjacent wherever you want to. You have to look at the angle they're talking about, B, and say, okay, opposite it is 3. And then what's this for? Well, this side of the 4, heck fire, that's touching my B angle. Okay, when you're touching somebody, you're adjacent. Like if somebody's standing behind you in the grocery line, they're adjacent to you. Okay, so we still have to find sine, so I still want to use so. And this time it's sine capital B equals opposite over hypotenuse. And remember, O means opposite, H means hypotenuse, S means sine. Okay, let's plug in our goods. Opposite is 3. Hypotenuse is 5. Hey, and that's sine capital B. The point of that was to show you, you cannot just throw the words opposite and adjacent on a triangle. The opposite actually has to be OPP, opposite of the angle you're talking about. Opposite of the angle you're talking about. Okay. We just played around with sine. Now we're going to play around with the rest of these. Let's go ahead. It says, find the 6 trig functions of, here's a right triangle, 5, 12, 13. And heck fire, that's one of those triples. 5, 12, 13. Okay. So first, we need to talk about where the angle is that I'm talking about. Well, here, the angle is not a capital letter. It's this 0 with a belt. Yeah. That 0 with a belt is called theta. Theta. I'm looking for it on this handout. Yeah, on the very front of your handout, it says theta, or that button, or that symbol is called theta. And those are angles. So angles are either capital letters, or we could use theta. Later on, we're going to use something called alpha and beta. And then even after that, we're going to use x's or y's. Okay. So let's go back. Okay, this theta is what we're looking at. According to the theta, opposite of it is this 12. What's the 13? Well, that's the crooked part. That's the slant. That's the hypotenuse. Remember, the slant is always the hypotenuse. And then the 5 is what's left over. Well, remember, this 5 side is sitting next to that theta. So it's adjacent. Yeah. So, like, if I'm standing right here and the IT guy named Jason is right here, we are adjacent. Okay? Okay. Because we're right next to each other. All right, now we're going to find the 6 trig functions. Well, that SOHCAHTOA thing, that describes 3 of them. So describes opposite and hypotenuse. Opposite over hypotenuse. Cosine describes the adjacent and hypotenuse on top of each other. Tangent is the opposite. Okay, you get the point. All right. So let's do sine. Sine. And then instead of putting the capital letter A for angle, or the capital letter B for the angle, we're going to use this theta. Okay. So sine theta equals opposite OH. Opposite over hypotenuse. Yeah. Okay, what's the opposite? What did we label it as? 12. What did we label the hypotenuse as? 5. Bam. Done. All right, now let's do cosine. That comes from the caca. Okay, so cosine is cosine theta. And then the AH describes the adjacent and hypotenuse on top of each other. If you're having trouble, we look at our second page of reminder handouts. And right underneath the triangle, it says cosine is adjacent over hypotenuse. Tan is opposite over... Yeah, you get that. Okay. Okay, adjacent is 5. Hypotenuse is 13. I don't even know how to say that. Okay. Let's go to tangent. Tangent is O over A. O, to, T stands for tangent. O stands for opposite. A stands for adjacent. Opposite is 12, adjacent is 5. Okay, we are not going to put this in the calculator and get decimals. If you look on that same page underneath SOHCAHTOA, under step 5, it says reduce the outside numbers of the fractions. Do not reduce the inside and outside of something with a square root. No decimals ever unless the question asks you specifically to estimate, guess, approximate, or round. Or some word like that. So anyway, the point is no decimals. Keep them fractions. All right, so these are our 3 trig functions. These are our 3 trig functions. Now we're going to find the reciprocals. And hopefully you remember the word reciprocal from college algebra means upside down. So that's literally what we're going to do. We're going to upside down all these answers and they become 3 new answers. Okay, so let's look for sine. Sine, his reciprocal starts with the opposite letter, C. And the reciprocal of sine, it says CSC. If you're wanting to know how to say that out loud, if at the very bottom it says, where's CSC? For CSC, we say cosecant. So this CSC, we pronounce it cosecant. Okay, and it is the hypotenuse over the opposite. Well, that's just upside down of SOHCAHTOA, sine. Sine is O over H. Well, we opposite it, H over O for cosecant. So let's go. Cosecant theta, and I put it right next to the sine just to kind of help me keep organized. But cosecant is the upside down of sine. So cosecant is 5/12. Because cosecant and sine, look at their fractions. They're just upside down of each other. Okay, what's the reciprocal of cosine? Cosine, it says SEC, and we speak that out loud by saying secant. Okay, so SEC is just going to be the flip of cosine. And the way I remember reciprocals is that their words start with different letters, like S and C, like those are different letters. S, C, yeah. Okay, so cosine is 5/13, but secant, the reciprocal, we have to turn that upside down, so 13/5. Same thing for cot. Cot means cotangent, and that's the upside down of tangent. So the upside down of tangent is 5/12. Hey. Okay, so for 6 trig functions, the first 3, sine, cosine, tangent, come from SOHCAHTOA. The next 3, cosecant, secant, cotangent, come from the reciprocals, or you just flip, flip, flip. Yeah, okay. The only thing is, be careful in the homework, because I think they rearrange these 3-letter words. Like they might have sine as the 8. They might have sine as the 4th answer they want you to type in. So just be careful when you're doing this at home. You label your goodies with sine, cosine, tangent, so that when you go to type it in the homework, you know what goes where. Because they will try and trick you. All right, we have another right triangle. This time theta is at the bottom right. And then it looks like I have a 9 and a 2. Well, first let's label opposite, adjacent, blah, 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 blah. Okay, so this 9 is the hypotenuse. Opposite of theta, well, it looks like it's not there. But then the adjacent, that's what is touching that theta angle. The adjacent is not the 9 because that's always the hypotenuse. Remember, the hypotenuse is across from this little box. Okay, so before we can whip through SOHCAHTOA, what does it say? Okay, we're going to look at this part of the tricks that say going backwards with SOHCAHTOA. It says when you are given 2 sides of a triangle, that's what we're given. 2 sides of a triangle. All right. The first step says label the, well, first let's just label opposite, adjacent, hypotenuse thing. Oh, we already did that. Okay. Step 2 says this fraction hoopla would be if they would have given us something to start with. So when it says fraction, like in these directions where it says, or when you are given a ratio of 2 sides that looks like SOHCAHTOA, that means they already give you the sign and the fraction. Okay, but for us, if they just give 2 sides of the fraction, 2 sides of the triangle, we labeled it according to, and now we're going to go to step 2, where it says use the Pythagorean theorem to find the missing piece. Pythagorean triples are common. This can save you time. Okay, well, I have a hypotenuse of 9 and an adjacent of 2. So let's go ahead and do our Pythagorean theorem. So we need to find our side. So I'm going to do a squared plus b squared equals c squared. And heck fire, this is like what we were doing 15 minutes ago. Where they give you 2 sides of the triangle and we have to find the third. So let's go. C squared is 9 squared always. C is always the hypotenuse. And then for these other guys, we don't really care what they are. They can be rearranged. So I'll just say that adjacent is A because it kind of makes sense. Plus B squared. And then let's math. We get 4 plus B squared equals 81. Subtract and we get 70. Don't judge me, I'm really bad at subtraction. 77, okay. And then we're gonna square root it. And the things that multiply to 77 are 7 and 11. But that's not a pair. Those are both prime. And it's not a pair. So we're just gonna leave that B as square root 77. And that sucker was the opposite. All right, now let's whip through the SOHCAHTOA. SOHCAHTOA. All right, so sine of the angle, our angle is theta, equals O over H. I abbreviated O and H. Opposite is square root 77. H is 9, and you cannot reduce the 77 because it's made up of a prime, 7 and 11. And you cannot reduce into the square root. If you look at that handout on the page of the Pythagorean triples junk, step 5, it says reduce the outside numbers of the fractions. Do not reduce the inside and outside of a square root thing. So the inside of a square root and the outside of a square root can never be reduced. So I'm not going to touch that 77 and 9. Okay, if we wanted to, we could go ahead and already start on the reciprocals. And remember, the reciprocals are just the upside down. So what was the reciprocal of sine? It was CSC. Because sine is opposite over hypotenuse, and CSC is backwards, hypotenuse over opposite. All right, so CSC theta, we're just going to flop this upside down. 9 over square root 77. But then, oh no, just like those very first problems we were doing, we cannot have a square root in the bottom. So you have to multiply by square root, top and bottom. Let's go. You're going to multiply by square root 77. Square root 77. Yep. Okay. And then CSC makes 9 square root 77 over, let's remember, a square root times a square root disappears. Kind of like on that handout, in this little box next to the word rationalize, number 4, it says square root 2 on the bottom, square root 2 on the bottom. That makes square root 4. And that pops out just a regular old 2. Yay. So for us, square root 77 times square root 77 is just a big fat 77. And I don't think you can reduce that 9 and 77. To try it, we can press 9 divided by 77. And then watch this. This is wicked. You press math. And it says arrow frac. That means take me to a fraction. And we want to go to a fraction. So press enter. And then enter again. And if it could have reduced, it would have changed. But mine stayed the same at 9 over 77. So that sucker's not reducible. Okay, let's go again. How about we try cosine theta? Cosine is ka-ka. Starts with C means the cosine. A means adjacent. H means hypotenuse. So let's see here. My adjacent is 2 over 9. Hot dog, that's it. Yep. And you cannot reduce that. Let's look for the reciprocal of CSC. Cosine. The reciprocal of cosine is SEC. And we call that secant. All right. Flip 2 over 9 upside down. 9 over 2. Hey-yo, done with that one. Okay, last sucker. Let's see. So we've done now we're on TOA. TOA means tangent of the angle, or tangent theta, equals O over A, opposite over adjacent. Opposite was square root of 77. Adjacent was 2. And those cannot reduce. And don't give me a decimal. All right. The reciprocal of tangent looks like cot. Cot means cotangent. So let's put cot theta. And then remember we reciprocal the tangent. So we have 2 over square root 77. But then bad news bears, you're not allowed to have a house on the bottom. Ugh. And we get 2 square root 77 over naked, plain, just regular 77. Let me actually, yeah, okay. So we multiply by the square roots of 77's top and bottom. And on the bottom, the square roots disappear and you just get a regular 77. On the top, they just squish up together. Hey, so we were supposed to find 6 answers. 1, 2, 3, 4, 5, 6. Good. Okay, let's go to C. Same-ish thing, but what is that? We got letters? I don't know. No, letters. Okay. I kind of like the letters better because you'll see. All right, so let's look at this angle. I got theta. According to this theta, what is that letter X? That letter X is the opposite. Well, according to this theta, what is this bottom piece? It's our adjacent, because we're sitting right next to that angle. It's kind of like when you guys are at a stoplight and you're in your cars. You guys are adjacent to each other. You're sitting next to each other. Okay. All right. It looks like we're missing the hypotenuse. Uh-oh. So we got to do the same thing we did on this last example. It's just going to be a little horrifying because it still has letters in it. Okay, so my first step is to find the side, which means a squared plus b squared equals c squared. Which one actually matters where I put it? Okay, the hypotenuse is always C. Always. Okay, so we don't know our C because it's the hypotenuse and it's missing. But then we know these other 2 sides, and it doesn't really matter which one you put first. I'm going to put the x square root 3 first and put parentheses squared around it. Just trust me. So put parentheses squared. If we don't put parentheses, we might forget to square the letter x. Okay, B is going to be the other leg of the triangle, that up and down piece, x. So put x square root 3 squared, okay, plus x in parentheses squared. And let's see what this makes. Well, when I square this x times x squared. Okay. And then I put a little multiply dot there because something's going to happen. When I square a square root, they cankle. So anytime you have a square root and you put some little 2 next to it, it cankles. Cankle. Yeah. So this square root of 3 squared, that cancels out, and it's just a 3. So the x becomes squared, and the 3 just comes out of the square root, comes out of the house, okay? Plus x squared, that's lame, that's just regular x squared, equals c squared. I think I taught this wrong in class. Oh no, 1 second. Oh no, I did a different problem. Okay, I'm okay. I apologize. All right, so we are going to get 3x squared plus, like my good friend Juan, x squared equals c squared. And then 3 plus 1 is 4x squared. Oh yeah. Equals c squared. Oh yeah. Put a house on it. Oh yeah. Okay, when you square root of 4, you get 2. When you square root an x squared, the tiny 2 and the house or the square root cancel. So you just get x. So our hypotenuse is just 2x. We're okay. Okay, so we got our side. Now, let's whip through our SOHCAHTOA. Okay, so for sine, we're going to say sine theta equals opposite over hypotenuse. The opposite is this x. The hypotenuse is 2x. Okay, the x's cancel. And you still have a 2 on the bottom. But what do you have on the top? You still have my good friend Juan that was secretly on that x. Yeah. So sine is 1/2. Okay, let's go ahead and do his reciprocal. I ran out of room. Dang it. I ran out of room. Okay, so let's go ahead and find the reciprocals. And remember, reciprocal means you flip it upside down. Okay, so what was the reciprocal of sine? The reciprocal of sine is CSC. And 1 over 2 upside down is 2 over 1 or just 2. Huzzah! Okay, now let's do the cosine. Cosine is adjacent over hypotenuse, or x square root 3 over 2x. Okay, the x's cancel because they're on the outside of the square root, so it's okay. And we get square root of 3 over 2. All right, let's flip it. The reciprocal of cosine is secant. So I flipped it to get my reciprocal, but then dag darn it, there's a square root in the bottom, so you gotta multiply by a square root. And we get 2 square root 3 over square root 3 times square root 3 is square root 9. Or just house times house, no house, 3. So secant is 2 square root of 3 over 3. Okay, now let's do tangent. Tangent is opposite over adjacent. And if you forgot where I'm getting these from, it comes from TOA. T stands for the tangent. O is what makes up the fraction. Okay, so let's plug in the goods. The opposite is x. The bottom is x square root 3. The x's cancel out. But when they cancel out, we have my good friend 1 at the top. But then, bad news bears, you can't have that square root in the bottom, so multiply by the square root. Okay, and we get square root 3 over house times house, no house. I think if you put that 1 before the square root, I think your homework doesn't count it right. So don't put the 1 before the square root. All right, now let's flip. For the tangent, I'm gonna flip the before math. And what I mean by that is, if you look at this tangent hoopla we were doing, The aftermath is this square root of 3 over 3 because it happened at the end. The before math is this what we got when we just plugged up into the fraction. Okay, so sometimes it's easier to flip the before math. Sometimes it's easier to flip the aftermath. I try and flip in a way that a house is not going to go on the bottom. So if I try and flip this aftermath of tangent, the aftermath, it came after at the end. If I flip it, the square root goes on the bottom, and then I'm gonna panic and bad things happen. Okay, but if I flip the before math, let's see what happens. So instead of x on top of x square root 3, we have x squared root of 3 on top of x. And then the x's cancel, and shablooey, square root 3. Hey. All right. Another one. Okay, we're not actually gonna finish this one. No, we are, my bad. All right, so let's see here. According to this theta, 1 is the opposite. 5 is the hypotenuse, or the C, because it's on the crooked piece of the diagonal, or it's across from the 90-degree angle. We're missing the adjacent, the side that's next to the theta. So before we can even do our SOHCAHTOA, I have to know the A for the SOHCAHTOA. I have to have my adjacent. So let's find our side. We're going to whip out the little Pythagorean theorem. A squared plus B squared equals C squared. And then A, I'll just keep it the adjacent, sure. So A squared plus the opposite is 1 squared equals the hypotenuse 5 squared. Okay, exponent, we get A squared plus 1 equals 25. Subtract the 1, A squared equals 24. Put a square root, put a house on that wicked witch. Reduce, or simplify. Okay, the things that multiply to 24 are maybe an 8 and a 3. And 8 is 4 and 2, and 4 is 2 and 2. Break up the cross out the 24, 8, and 4 so that we don't accidentally write it somewhere. The pair goes on the outside, so that's a 2. The singles go on the inside with a multiply dot. All right, so our little a is 2 on the outside, 3 multiply dot 2 on the inside, or just 3 square root 6, and that's our adjacent. Okay, let's go ahead and whip through the SOHCAHTOA. And then we'll flip them to do the reciprocals. Okay, sine of theta is opposite over hypotenuse. So the opposite is 1, the hypotenuse is 5. Ba-bam! Okay, that's done. Let's go ahead and try his reciprocal. What's the reciprocal of sine? The reciprocal of sine is the one right next to it, CSC. And they're reciprocals because their fractions are upside down of each other. Opposite over hypotenuse, hypotenuse over opposite. Those are called reciprocals. Okay, so the CSC is the reciprocal, and it's flip 1 over 5 upside down. You get 5 over 1, or just 5. Yeah. Okay, let's do cosine. Cosine theta is C and then AH. So A over H. The adjacent is 2 square root 6. The hypotenuse is 5. You cannot reduce the 2 and the 5. So you just stop there. All right, the reciprocal of cosine is secant theta. And we're gonna flip this bad boy upside down. So 5 on top, 2 square root 6 on bottom. Bad news bears, you can't have that square root 6 on the bottom, so let's multiply by square root 6. Just square root 6. And you get 5 square root 6 over, there's already a 2 there, multiply dot, house times house, no house, just regular 6. And then math it out. So we get 5 square root 6 over 12. Hey-oh. Okay. Last one. Tangent theta. Remember, tangent is TOA. T for tan, O for opposite, A for adjacent. Opposite is 1, adjacent is 2 square root 6. Bad news bears, you can't have that square root on the bottom. On the top, we don't write 1 square root 6 because we're grown up. We just write square root 6. I think your homework counts it wrong if you put the 1 there. Okay, and then on the bottom, we have big fat 2 already there. Multiply dot. Square root 6 times square root 6 is square root 36. And hey, that's just 6 again. Or house times house, no house. And then that finally pops to square root 6 over 12. And then don't forget those tricks said on number 5. Do not reduce the inside with the outside, ever. So I'm not reducing this 6 and 12 because one's on the inside of a square root, one's not. All right, now let's do the reciprocal of tangent. It's cotangent. So let's think about this. Either I could flip the before math of 1 over 2 square root 6, or I could flip the after math. It doesn't matter. It's whatever you want. I think if I flip the aftermath, the house goes on the bottom, and I panic about that. So let's look at the before math. If I flip this, the 1 goes to the bottom, and the house goes to the top. That's good. Yeah, let's flip this before math. So instead of 1 over 2, we're going to have 2 over 1. So we flipped the before. And we could have flipped the after. It would have just taken a minute. Okay. Because we would have had to reduce. And then this junk divided by 1 is just the same old 2 square root 6. Okay, I'm going to go ahead and pause and upload this video because it's too long.